see. So you conclude from this that therefore, look at, here's the wave equation on a string. Here's a wave like this. The velocity of the wave is this v, 1 over v squared. So you conclude that Maxwell's equations tell us that the electromagnetic field is also a wave, and the velocity of this thing has to equal 1 over the square root of mu naught epsilon naught. And when you put in mu naught epsilon naught, you get 3 times 10 to the 8th meters per second, which equals c. Which equals c.
C.
Well, thank you. Right? So when you can do this, you understand it. If you can't do these steps, you don't understand it, in my opinion. Right? You can talk about it and everything, but you've got to be able to get there.
So like if that's giving you the velocity for the...
Yeah, so it's giving you two things. It's one, no, we're not there. We're looking at just the velocity of the electromagnetic field of light.
Oh, okay.
All right? And so we're building up to the electron. All right? If you do the same thing, you take the curl of this one, then you'll end up with the same equations for B. All right? And you'll find out that B is an electromagnetic wave with velocity c. And then when you do E and M2, and I'm not being so careful with all the vector aspects of it right now, but when you solve for B, what you find out is the following. So here I'm going to say this is X, this is Y, and this is Z. So I'm using the right-hand rule, X, Y, Z. All right? That if what you find out is that if this represents the electric field, so I should have made it the same amplitude. There's the electric field. All right. The magnetic field is going to be in the Y direction, and it's going to look like this. So it's going to be in the Y plane. All right. And so here we go. We have the electric field right here, and this is the magnetic field B. Right, there's the electric field and the magnetic field B. And then what you discover then is that light is a self-perpetuating electromagnetic field. What happens, and this is, Jeremy, the thing I wanted to bring to you because of your early question, what light really is in a vacuum is just these electromagnetic fields. When the E field changes, the changing E field makes a B field. When the B field changes, it makes an electric field change, and it just goes on like that forever. So as long as the electric and magnetic field are changing, you have the self-propagating plane wave, and that plane wave travels in the Z direction, and the velocity of that plane wave is equal to c.
And you can get that through the pointing vector? Or? Yeah,
so the pointing vector is E cross B, and that gives you the direction of the plane wave, and also you can get the power out of the pointing vector. Okay? Okay. So, I guess I didn't write out the solutions for these. The solutions equal E0 e to the I kx minus omega t in the x-hat direction. For B, what you get is B equals B0 e to the I kx minus omega t in the y-hat direction. So that's I kx minus omega t. All right, and these solutions, e to the I kx minus omega t, equal plane traveling waves where omega equals 2 pi times the frequency. So this is the frequency of that wave, and k equals 2 pi over lambda, which equals the wave number. All right? But here's a better way to say it. I always think this is the angular frequency, and it's in the units of radians. per second, because frequency is 1 over second, and k is the spatial frequency. It has units of radians per meter, or radians per length. All right, so let me get this in a different form. I can also write omega is equal to 2 pi over the period. So maybe this is a nice one. So now we have, if this is plotted as a function of time, not t, then the period is the time of one complete wave. And then when it's plotted as a function of space, the spatial dimensions of one complete cycle is the wavelength, right there. All right, so see the connection between those two and the actual wave, the period and the frequency of the wave? The period and the wavelength of the wave. Okay? It's a little bit troubling, I think, sometimes to think about what a plane wave really is. Let me do one other piece of algebraic magic. All right? So check this out. If I take e to the I kx, I can go e to the I k. So I'm going to factor out a k minus omega times t, omega over k, right, times t. Factoring that out. So I recognize that omega over k is 2 pi over the wavelength, all divided by 2 pi over the period, divided by 2 pi over the wavelength, which equals wavelength over a period. So what are the units of wavelength over a period?
Velocity.
The velocity. This is the velocity. So omega over k equals a velocity. So in other words, e to the I kx is also e to the I k times x minus vt. Throwing a lot of stuff at you here today. There's lots and lots of. Go ahead.
So is it just like another way to look at it? Like it's something that could be used?
Well, here's the deal. The reason I'm doing it, Dina, is because what do you know about any function of x minus vt? So in other words, this equals a function of x minus vt. Isn't the x naught versus whatever you
Displacement, right?
Okay, it's like a displacement, right? But essentially, that's the definition of what makes a traveling wave. Yeah, is if you're a function of x minus vt, that defines you as a traveling wave. Alright, let me see if I can make a little sidebar over here to show you that.
What is that, radians over L?
Say that again, please.
What is that, radians over L?
Over length, the dimension of length. Okay. So when I put in square brackets, so square brackets are dimensions. So this is the dimension of length. Alright, but let's see. Any function of x minus vt equals a traveling wave. Alright, let me see. I'm doing this off my head, and it's sometimes hard to get this picture. So, so let's say at t equals 0, so this is at t equals 0, so it's f of x. Alright, so there's f of x. And then at some later time t, okay, the wave looks looks like this, it's a plane traveling wave, so it looks the same. And this is f of x minus vt. All right. Now, if you think about this distance right here, if this is a wave, right, and it's traveling at a velocity v, how far has that wave traveled from here to here in a time t?
Distance x.
At x, and x equals
P to P.
velocity times time, right? So this distance right here, x equals velocity times time. All right, so essentially what this is saying that if you take this function of x, here I am at some time x right here, and I subtract from x an amount given by velocity times x, velocity of x equals velocity times time, then that takes this wave and puts it right back here. Which means it's the same wave that it was here, except for it's propagated over here by velocity v.
So that formula, in essence, propagates that x?
Oh, that's a nice way. So by going to minus the vt, it propagates. It propagates the shape. All right, and it's a general result. I am pretty sure this is in Griffiths. Okay, who's had electrodynamics? Raise your hand.
It might be in part 2.
Okay, it's in Griffiths.
It's in part 2.
It might be in part 2 though, okay? But Griffiths does a fantastic job of explaining this even better. But the key result is any function of x minus vt is a wave. Right? Is a traveling wave. So what the solutions over here, what I did by factoring out k is I just showed it was a function of x minus vt. So the solutions are waves.
Wouldn't it? X minus vt. So a function of x minus vt where x, v, and t are all changing.
So in this case, time is changing. This is x, right?
X. Are you talking about x, like where it is now? Okay.
So a traveling wave of a velocity v. So check it out. If I have this shape, right? And it's at x equals 0. Where is that shape at some time t?
That whatever velocity is times
time. Yeah. And so what this is saying is, look, here I am at that place x. Right? If you subtract from x vt, which is how far I've traveled, it'll bring me back to x equals 0. Bring me back right there.
So wouldn't it just end up with 0 each time? If you're counting x as where you are, v is how fast you're traveling, and t how much time has elapsed, like wouldn't it just end up with 0 each time?
Well, yeah, units are canceling out. You're getting a length minus a length, but it means something because you're going at a velocity, and that's showing.
What it means is that any x you're at, the shape of that function is going to be the same thing that you were at x equals 0. So this should be maybe something like f equals 0 at f equals 0. There's my shape. Okay? At some time later, right, at some other distance, then this is always going to come out to be the f of 0 is going to be the same shape of what I was at x equals 0.
Okay.
Okay. Look, I don't want to go into too much more. Let's go into Griffiths electrodynamics, and you can read more about it. And it probably should be in an introductory book. All right. But the big point is that the solutions to the Maxwell's equations. So look, it's a mess. E to the I kx. What does that mean? All right. Well, the first thing that we're pulling out of it is the E to the I kx minus omega t. It's simply x, some function of x minus vt. So it's some wave that travels with a given velocity.
Or like a solution for a secondary